Well, good morning, everyone. I see our attendees are starting to trickle in here. And good afternoon to everybody joining us over in Europe. It is my pleasure to kick off with a quick hello. My name is Thomas Green. I'm a technology manager in the Hydrogen Fuel Cells and Technology Office in the Department of Energy. I was tasked with starting this working group for clean steel production using clean hydrogen by our director, Dr. Sunita Satyapal, because she believes deeply in the growth of end uses for clean hydrogen and including in the industrial sector, clean steel definitely leading the way there. As well as the mission innovation focus, which is making sure that we are collaborating across the world, across countries, so that we can kick off these technologies and spur growth faster than if we were to just do it alone. We've seen other successful working groups across other end uses for clean hydrogen under the Clean Energy Ministerial, such as for off-road transportation. And we're hoping to replicate that success for hydrogen in clean steel production. This is the first of our public webinars that we are hosting, and we will have a bunch coming up later this year and into next year, so that we can continue this dialogue that we've started with our stakeholders on how to jumpstart this growth of clean steel in the United States. It's my pleasure to be joined by our colleagues in the national labs who will be introduced shortly. And we wanted to focus this webinar on a topic that I've found really interesting and really exciting as we've dived more into it, and that is how to produce clean steel while thinking about how it interacts and can support a clean grid, and even the opportunities for going off grid and having a siloed hydrogen production facility. So without further ado, I'll pass it over to my colleague, Rebecca, who will introduce the speakers.
Sure. Thank you, Thomas. Hi, my name is Rebecca Irwin, and I am a technical project officer within the Department of Energy in the Hydrogen Fuel Cell and Technologies Office. And I'm very honored to present our first speaker, which is Dr. Jennifer King, who is a distinguished member of the research staff of the Wind Hybrid Systems Group Manager at the National Renewable Energy Laboratory. And she will be presenting work on designing purpose-built renewable energy systems with electrolytic hydrogen, specifically focusing on iron and steel decarbonization with clean hydrogen. So I will pass it over to Jennifer. Thank you.
Great, thank you so much. As was mentioned, my name is Jen King, and I have been working together with Steve Hammond on this project on hybrid energy systems to hydrogen to green steel. And I'm excited for this opportunity to present this work to you. So our goal so far here is to develop reference designs for gigawatt scale off-grid tightly coupled hybrid systems that are purpose built for some end use, green steel in this particular case. So how does bringing together all technologies at the same location impact their ability to be deployed? Now, this is a large team effort, and I've listed the other labs that are integrated into this project as well: LBNL, or Lawrence Berkeley, specifically HANA here, Argonne, Sandia, and Oak Ridge, and there's several NREL contributors as well. And this map that I have up here shows the hubs and shows them co-located with hydrogen storage, which will become a critical part of this presentation as well as the next presentation. And just showing kind of, it really matters when we start talking about where these systems can be deployed and how rapidly. So building on that, why is this important? Why does it matter if we co-locate and bring all of these technologies together? From my perspective, it's the time to deployment can be reduced. And how does that happen? Integrated H2, or again, bringing all of these technologies together and having them coupled and integrated, provides an accelerated deployment path that opens up new locations that lack grid infrastructure. So if we need to electrify all sectors, buildings, vehicles, and industrial decarbonization, that's going to require a massive grid build out. these types of systems that are co-located could maximize the use of existing infrastructure and open up new pathways for this to be deployed today. The co-location of assets can provide extra cost savings, whether that's through balance of station or novel integration technologies across heat or power electronics or others, and also provides for cross-sector coupling opportunities. Now, the use cases that we have considered when we do this modeling and analysis are these three that are pictured here. The first one is fossil fuel based, so using steam methane reform to produce hydrogen. And then we examine both steel and ammonia as an end use. I'll be focusing on steel today. The second use case is using PEM electrolyzers, but they're connected to the grid. And then they produce hydrogen that goes into the steelmaking process. We've also considered co-located wind or solar or other renewables, but backfilled by the grid. And then the last one is an off-grid hydrogen production. The steel plant is still connected to the grid, but off-grid hydrogen production, again, so we take some of that burden off the grid. Now I like to show this map because it really brings a lot of the data together that we need to rely on in order to look at these systems, and it shows the complexity of looking at the full system and how it differs based on the location that you choose. So here we have the renewable energy potential in blue. Darker blue is better renewable potential. You have hydrogen demand centers in the orange, which is ammonia, and the black, which is relevant for this conversation, which is more the syn fuels and metals. And then you have water scarcity in the brown areas, and then you have geologic hydrogen storage potential in the salt caverns, which is the gray outlined, and then lined hard rock, which is in the black hatched areas. And we've done a deep dive on these 5 different locations that I'll talk about. We've done Minnesota that has suitable renewables, potential for lined rock caverns and access to raw materials. Iowa has good renewables, access to existing ammonia pipeline, but no geologic storage. Indiana has pretty good renewables, largest steel mill in the US, but no geologic storage. Texas has excellent wind resource and access to salt caverns, but is in a water stress region. And the last one is Mississippi. While it doesn't have the best renewable potential in the US, is close to existing demand in salt caverns, which is a big part of it as well. So before I get into the results, I want to provide some of the key insights that you'll see throughout the presentation here. One is that hybrid system designs matter. So bringing wind and solar together can significantly reduce LCOH. And the reason is, in a lot of places, wind and solar are complementary. So it's windy at night and sunny during the day. So you just have more hours of operation, higher capacity factor for your electrolyzer, reducing storage requirements and reducing degradation. Second thing is that the IRA policy is a game changer for this integrated H2, like co-located wind, renewables, hydrogen, and end use. We do consider stacking policy across renewables. So you have the wind PTC, solar ITC, the storage ITC, both on the battery and hydrogen storage side of things, and then the hydrogen PTC, which at its maximum is a $3 per kilogram credit. A few other things to note here is that integrated H2 costs are highly site specific. It's really driven by the wind resource more than the solar resource. That has a substantial impact on LCOE and therefore LCOH. And again, these off-grid deployments enable more deployment options that don't rely necessarily on having grid access. Cost of hydrogen storage is the big driver for LCOH, especially when policy is not enabled, and directly coupling these renewables, meaning not having the grid in between technologies can provide significant cost savings. So moving into the results here, I'm just going to take a deep dive into Texas in 2030 and talk through some of the results that we've been seeing, and then we'll go kind of to the broader 5 locations that we looked at. So here we have our first use case, which is the first 2 blocks, which is fossil fuel-based approach using steam methane reform. And then another option was steam methane reform plus CCS, carbon capture sequestration. And the carbon capture sequestration is eligible for a tax credit as well. And that has been applied here. And that's shown by the gray bar pushing the cost lower. So this is the cost of hydrogen, in particular, I didn't mention that up front. And we're kind of using steam methane reform as the baseline to understand how all of these other types of scenarios compare. There are several assumptions that went into this analysis, which I'll talk about on the next slide after we go through these. But the next one is, the next use case is on the grid. So we have a grid only case, so grid connected to PEM electrolyzer feeding into a steel making facility. And then we have wind plus grid. So you have a wind plant co-located with your hydrogen backfilled by the grid, and then grid plus wind plus PV. And those cases are heavily dependent on the grid, the retail price assumed for this particular location. So these 3 bars actually have some pretty wide error bars that I'm not showing here, error bars, uncertainty bars, depending on retail prices. And then the last one is off-grid configurations where you have wind only connected to electrolyzer, wind plus PV plus battery connected to an electrolyzer. And then the last one is if you put an electrolyzer into a wind turbine or right next to a wind turbine, are there any significant cost savings here? In this particular location, we didn't see that, but there could be potential savings down the line, especially if you go offshore. A few more things to note here is that off-grid costs are less than on-grid because, in this particular case, because electricity costs are lower. And again, this comes back to what is assumed as the retail rates. We do allow for dynamic operation of hydrogen in this analysis, and it is accounted for in the increased replacement costs, although those are low in this analysis. And we do, for Texas in particular, this has, as a reminder, this has access to low-cost hydrogen storage in the form of salt caverns. And the last thing I'll note here too is that the gray lines are the maximum policy for the IRA, and then the black arrows are the base policy. So you get a 5x multiplier depending on prevailing wages and things like that. So we're just showing that range of potential. Now these costs do go, these costs do go negative, and that has to do with our assumptions on financial parameters. We're keeping them the same across all locations, and this will have to be looked at in the future. Okay, now bringing all of the locations together. I've mentioned some of these high-level assumptions, but I want to be clear here before moving forward, and these results are preliminary. We do use publicly available data for cost for raw materials, cost for transportation, wind resource using the wind toolkit data, solar resource using solar, the NSRDB, and so on and so forth. And so these types of analyses can be further refined with local knowledge and local data. We use the annual technology baseline from the Department of Energy where applicable. Electrolyzer costs are based on HFTO from DOE's projections. Electricity prices are difficult to forecast and are based on a decarbonized grid and our retail prices. Current supply chain limitations are not represented. So if it takes longer to get electrolyzers and things like that, we don't account for that in replacement costs. We are considering specifically new builds of DRI plus EAF and the costs are adjusted for specific cases. So as I showed in the previous plot, these are the different scenarios that we looked at: fossil basin on the left-hand side, grid only in the middle, and then off-grid on the right-hand side. And you can see for 2025, or very near term, that we have SMR is able to provide the lowest cost steel prices across all of the locations. And I just want to keep, we won't go through all of the scenarios for all of the plots. I just want to keep an eye on a few of them. Here's an on-grid use case with wind and solar, and then we have an off-grid use case. And we'll just be comparing these three across as we move forward in time and as we apply policy. So on-grid here is cheapest of the two. Then we start moving into 2030, and costs for specific renewable technology and hydrogen PEM electrolyzers goes down. And so off-grid starts to become cheaper. But again, these are based off of projected retail prices and could be adjusted in the future. And then similar for 2035. Now this is with the actual policy implemented as well. So base policy is what we just saw, or sorry, no policy is what we just saw. Maximum policy is what we see on the bottom. And you can see that even starting in 2025, some of these green steel, so with PEM electrolyzers, start to become cost effective. And so that's shown by the dotted line across. And so you start to see a few scenarios that start to become cost competitive, and even the grid cases could become cost competitive depending on the retail prices. And in 2030, you're really starting to drive down that cost further. And one other thing that I'd like to note, though, is that these policies do provide a window of opportunity, and without the policies, the cost goes back up, and you can see that it that with the current cost projections in 2035, fossil-based approaches or steam methane reform becomes cost effective again, more cost effective again. So IRA makes this possible in the near term, and there's a window of opportunity here. Now, these end-to-end capabilities for green steel that we have developed allow us to take a nationwide view as well. So using high performance computing, these models, when you stack them together, become a little computationally expensive, but this was looking at 50,000 locations across the US and looking specifically at hydrogen production. And we can figure out where low cost hydrogen can be deployed to support some of these end uses. And here we're showing all the locations where it's sub $1 with maximum policy, and other metrics we can look at too is hydrogen production in some of these areas. Lowest cost doesn't necessarily mean the most hydrogen produced. It depends again on the operating hours and so on and so forth. And the last thing I'll note too is each of these individual locations is optimized for wind, solar, battery, and electrolyzer ratio sizing, which is why the hydrogen production changes across the nation. Some of the other things that we have looked at too for these types of end uses that require steady state operation for hydrogen production or hydrogen delivered, I guess, is the storage. And I just want to tee this up as well. With Hannah's talk next, is that the hydrogen storage really matters, and it matters where you are in terms of how much storage you need. So depending on where you are in the US, this is driven by capacity factor, complementarity of resources, and so on and so forth, about how much storage is needed to provide a steady state. Now, this is a conservative view because we don't assume outages and things like that. So I think the important takeaways is that there is a range here, 8 to 20 days of storage that's needed for some of these steady state end uses like steel, green steel in particular. I just want to provide an overview of where we're headed. So I talked about our detailed system design and analysis work so far, and our work towards the national roadmap with location-specific reference designs. We are in the middle of this phase right now, and we will be moving into demonstration and validation in the future to demonstrate some of these integrated concepts. The last thing I want to note here is from this research, we have developed some pretty key future research questions, at least from my perspective. And the first one is having an integrated modeling and demonstration platform so we can look at some of these concepts, de-risk and accelerate deployment. Low cost storage. We're currently limited to access to geologic storage due to cost. Dynamic and flexible end uses could also be a game changer and reduce the need for seasonal storage. Coordinated controls across all of the technologies, controlling the flow of electrons and molecules across the integrated system will be really important. Novel integration and system designs to take advantage of synergies across technologies, things like heat integration will be critical to drive down costs, and sector coupling. Maybe pairing together things like steel or cement and concrete could be helpful to reduce costs and infrastructure needs. It could have shared hydrogen storage, for example. So with that, I'd like to conclude my section of the talk by giving a summary of where we've been so far. The hybrid system designs with wind and solar can significantly reduce LCOH. IRA is a game changer for this integrated H2 concept. They're very site specific, but can allow for off-grid deployment, and the cost for hydrogen storage is a big driver for LCOH. Didn't mention it a ton during the presentation, but there was a huge spread between projects that would be built where there's salt caverns versus where there's no storage. And then finally, directly coupling renewables to hydrogen, meaning not having the grid in the middle provides significant cost savings. So that, I'd like to thank you for your time, and I'll pass it back over to you all, Thomas and Rebecca.
Great, thank you so much, Jen. This is a great presentation. I wanted to give a reminder that if you have any questions, please use the Q&A feature. And these presentations will also be recorded, so you can watch them down the line. And with that, I will introduce our next speaker, Dr. Hanna Brunig. She is a research scientist at the Lawrence Berkeley National Lab and deputy leader of the Sustainable Energy and Environmental Systems Department. And she will be presenting work on hydrogen storage technologies and economic considerations, specifically for locations that do not have accessible use of geologic storage and in these considerations for steel specifically. So with that, I will pass it off to Hannah. Thank you.
Thank you so much, Rebecca, and thanks, Jen, for setting up the topic and with such great figures. So my name's Hanna Brunig. I'm a research scientist at Lawrence Berkeley National Lab, and I'll be presenting work that is things that we started back in 2020 as collaboration with research scientists at Argonne National Lab, Pacific Northwest National Lab, and now NREL, Renewable Energy Lab. And so the work has evolved over the time. We've learned a lot since we started, but overall, I'll be giving some of the insights into the various hydrogen storage systems, what the technical targets are for the iron and steel industry in particular, and some of the work still to be done to help scale up these systems. So hydrogen has been used in large-scale industries for quite a while, for decades, but we're seeing a transition now in not only the end uses of hydrogen in large-scale industry, but also moving from the sources of hydrogen, from pure hydrogen end use that's coming from fossil resources, to hydrogen being delivered by a syngas, which is a combination of carbon monoxide and hydrogen produced from methane, most likely, to now renewable hydrogen, as Jen presented, So there are outstanding questions around how are we bringing renewables to end users like industry that have very steady demand for that energy or that feedstock. And that's where the hydrogen storage piece comes into play in a unique way, despite we have a lot of history using hydrogen in large volumes in industry already. So we want to deliver the renewables of wind and solar, as Jen presented. We want to be able to have reliable delivery of that energy. So it's not only about smoothing daily and seasonal variations, it's also about backup reliability of feedstock and be able to meet the demand of that end user. And so this required us to do a bit of a campaign to understand the needs of iron and steel facilities for hydrogen demand, and understand the flexibility they have in that feedstock, the purity they have in that feedstock, the rate of delivery, the pressure and temperature. All these things affect ultimately the delivery of that hydrogen. And in cases where we're not just having a pipeline go directly to the iron facility, there might be co-location of production. There are questions around whether that hydrogen is coming straight from the electrolyzers, from a pipeline, or from hydrogen storage. So these things all affect the ways that hydrogen is being coupled into the system. And so there are a lot of questions to be answered about what does that do to cost and technical viability. So why is it a big deal to talk about hydrogen storage these days? Well, hydrogen is tricky. It's a tricky thing to move and it's a tricky thing to store. It has very low volumetric energy density at ambient temperatures. And so often you hear about hydrogen being cryogenically stored to increase its density or compressed to very high pressures, such as 350 or 700 bar systems. But even then, these systems are challenged by the amount of energy it takes to offer that level of density. And even those levels of density are not necessarily good enough for the end user. So there's been a lot of advancements to develop many, many different types of hydrogen storage systems. And I often think of this parallel to the battery world, where there's many, many different batteries that have evolved to meet the needs of the end user. And we're now in this really novel time period where we are understanding the needs of the end user and co-designing the storage system to be able to meet these needs. So I talked a little bit about physical-based hydrogen storage, cryogenic liquid, compressed gas, and combinations. There's also materials that are being developed that can store the hydrogen in very high densities, often at near ambient conditions. And so this is really compelling for safety reasons as well as for cost reasons. So some of the most common ones you'll hear about are adsorbent materials, which often require some cooling to get the hydrogen stored onto them. You can think of them as a crystalline structure that's packed into a tank. Hydrogen is flowed in, it adsorbs, and it's stored there until it's released for end use. There's also liquid organic hydrogen carrier systems. You can think of these more like reactions with a catalyst-driven reaction. So it's almost like a little bit of a factory where you take hydrogen, you convert it into something else, you store it pretty much in ambient conditions most of the time until you need to react it back to hydrogen. And there's other materials to go into. And today I'll be talking about a couple different types of hydrogen storage at scale, including organic carriers. So as I mentioned at the beginning, we are in this interesting period in time where we are learning so much about the needs of hydrogen storage. Like Jen provided, we now understand what number of days of storage we need for different locations in just the United States, and understanding what that means for the size of the system. But on the end user side, we also understand the rate of delivery needed, the reliability needed, the purity needed. And so all of these things from the market trickle down. And what my team does is we translate those needs into material targets and properties for the engineering system. And this is what the Highmark Department of Energy Consortium does, is we validate materials, we develop materials, and we screen materials for promise. So some very recent new work out of the team, published in 2023 in Energy Environmental Science, was a whole facility analysis of iron and steel facility based on DRI, or direct reduction of iron system. Now, those have been demonstrated with syngas, with methane, but they're just now starting to be demonstrated with pure hydrogen. So we're still learning a lot about the system, but we were able to do enough of an engineering analysis to understand what the needs were, what the technical targets and delivery rates would be, with ultimately the goal being to produce a green steel product at market price with significantly lower greenhouse gas emissions than what could be achieved with today's systems, or potentially even natural gas with CO2 capture, as Jen noted, was a benchmark system. So in our starting work, this was a lab call funded by the Department of Energy. We were tasked with doing a full design and evaluation of a liquid organic hydrogen carrier system. We'd had the models working with Argonne National Lab to look at salt caverns, to look at rockline caverns, to look at cryogenic liquid storage, to look at compressed gas storage, but we hadn't fully taken the step to model what the costs and performance of a liquid carrier would be. So that's what we did. And we chose an example location where we knew the wind and solar profile to be able to help us just build the mathematical model. And ultimately, we got to a point where we're now able to take those 50,000 data points that Jen noted and start to rapidly screen them to model the systems through scaling factors that I'll discuss in the coming slides. So what we did is we took a location, we estimated the production of hydrogen, assuming some target cost rate or modeling it, and we looked at the amount of time that the electrolyzers could deliver that hydrogen to the end user. So for a medium-sized iron steel facility, we ballparked around 200 metric tons per day of hydrogen would be consumed, had to be delivered reliably. Now, the reality is the electrolyzers cannot always meet that demand. It would be too costly to oversize them to do that. And there are times in the year when there's not enough solar, there's not enough wind to deliver that amount. The solution was to develop a hydrogen storage system that during periods of excess renewables, we stored enough hydrogen so that during the periods of limited renewables, we were able to deliver that hydrogen at least 200 metric tons per day to the steel facility. So that's the example system we have. We're about 25% of the year, we're actually delivering that hydrogen from the storage facility. So we were tasked with that extreme case where the storage facility had to deliver all hydrogen during some cases. Now that's an assumption because there are many cases where the electrolyzers will always run at some level. So those are variables that we're playing with now. What we found is, again, assuming you hit the $1 target that the DOE has as a goal for hydrogen production, what is that added cost of storing your hydrogen? So we found if you look at the amount of hydrogen flowing directly, that's delivering $1. If you look at the amount going through the storage facility, and that storage facility has an added levelized cost of about $1.25 in this case, your annualized amount that you actually have to pay over the year is about $1.31. So in effect, the storage system added about 31 cents to your cost. So that was our starting point. We compared that liquid organic carrier, the toluene in gray, with the other systems. We found the geologic systems were by far the cheapest, but the liquid carrier was surprisingly one of the winners, and it looked substantially better than cryogenic systems or compressed gas storage. This inspired us to go further, to look into details of the storage system, to look into the engineering system, and understand where we could cut costs further, or also look at some of the vulnerabilities in our assumptions. So this is kind of the breakdown of how the system was modeled. So in this scenario, the wind was varied with solar. So it was a bit of either a pure wind system, 100% wind, or 100% solar, or some combination. And we found in this example, at a 31% wind fraction, we were able to achieve the lowest cost. So we assumed that the storage system had to deliver 200 tons per day. We looked at the necessary wind and solar sizing to be able to deliver the amount of hydrogen we needed. We looked at the capacity, and we looked at the peak amount of hydrogen that is produced from those systems. Now, some of that is going to the storage and some of that is going directly to the facility. Ultimately, that helped us size our storage system. And you can see the way I'm going to talk about the liquid carrier is you have decoupled systems. You have that reaction to take your hydrogen, turn it into methyl cyclohexane, and you have the reaction to take that methyl cyclohexane, which is stored, and turn it back into hydrogen. So delivering the hydrogen is what we call dehydrogenation, and that is always going to have to be at 200 tons per day, the end user's need. But the hydrogenation plant has to be able to store the hydrogen year-round at the peak amount from the wind and solar. That's why it's bigger, at least on the capacity side. So how does this compare with the needs of the steel plant? Well, when we modeled the steel plant looking at the use of hydrogen just to deliver heat demand, we ultimately were competing with our natural gas. That's what currently we're assuming is providing heat. Well, that's really tricky. Natural gas is pretty cheap. And ultimately, your delivered cost of hydrogen is basically going to be near that $1 delivered target. So there's not much room for the cost of storage to be added on to your $1 to meet the needs. So that is a really tricky case. However, if instead of using that precious hydrogen for heat, you're actually using it to directly reduce the iron, now you have an interesting system where you actually have more space to have a higher cost hydrogen delivered and still break even with your competing systems. So that leaves about a 70-cent per kilogram of stored opportunity for the delivery and storage of hydrogen on top of your production system. So that was really interesting because, again, that is the annualized amount, which translates to about $2.80 for the levelized cost of storage. And we have materials today that can hit that target. That's what's really exciting about this research. So this is a process flow diagram of that methyl cyclohexane toluene system. A lot of this was inspired by a 2021 paper published by the Argonne National Lab, as well as a system provided by Chiyoda, where Chiyoda actually has 2 locations. So they're shipping it. So they're hydrogenating in one location, shipping that MCH on a vehicle like a boat, and then dehydrogenating in another country or location. Here, we are co-locating those systems, so it required a remodel. The work we're doing today is we're changing things about how heat management is being considered. We have new catalysts coming out of the HYMARC system teams that we're looking at, and we're gathering new intrinsic properties to help us further understand these systems to better improve the robustness and scale of the system. We're also looking at the effect of these 50 locations, the needs of those locations on the cost of this system. We've consulted with the Pacific Northwest Department of Energy Hydrogen Safety Panel and understanding the needs of what it would look like, the land footprint, the regulations, and all of that for a whole system analysis. We're also thinking about the life cycle of this system. So if this system is run on electricity, it could be the renewables, or it could be grid electricity, it could be natural gas. These things all affect the carbon intensity of your hydrogen. And in today's world, where we have the IRA tax incentives being driven by carbon intensity, it's very important for us to understand these impacts. So if you are using clean electricity, like renewables, you're going to be able to hit your targets versus if you're using the average US electricity grid. So these are all considerations to take into account. And that's just for the production of hydrogen. Now, for the MCH toluene system, we have added electricity demand on top of your electricity demand for producing hydrogen. You also have heat demand, which will probably come from natural gas. Using hydrogen is probably not going to be viable. And then you have your CO2 emissions that are coming from your electricity demand and your natural gas consumption. So the breakdown of the costs, we look at this 2021, 2020 model from Argonne, we modify it with heat management, and we look at more conservative values based on Chiyoda's protection of their catalyst bed system. This all leads to delivered costs of storage. Now, if you remember, our target was 71 cents. So again, very exciting that we are within range as long as, and this is the big as long, we could hit a $1 hydrogen production target. And that's not, that is taking into account tax incentives that could help us reach that $1. So key findings, I would say, is the hydrogen carriers are competitive in this application. They can meet technical requirements. They're on the same order of magnitude as geologic hydrogen storage. In some locations where you do not have geologic storage, you could potentially use a hydrogen carrier system. This is still emerging technology. We've not demonstrated carriers at this scale, so there's a lot of excitement around building up demonstrations that can improve, let's say, the market's confidence in this technology solution. We've looked at the co-location of storage at the iron and steel facility, and we would say overall, the benefit of co-location is not very clear. So if the hydrogen storage system was located closer to the renewables rather than at the iron and steel facility, there wouldn't be a big penalty on cost per se. Key here in the cost assumptions is that the system can provide backup, reliable feedstock. So this is not just about boosting your capacity of your renewables. This is about providing, in cases where the electrolyzer is completely shut off, all 200 metric tons per day of hydrogen. If you can play with that assumption, your costs go down a lot. So those are the kind of scenarios we're going to be looking at in the coming year. And I would say, finally, there are many different materials aside from the MCH toluene system that are developing out of startup companies, out of national labs, out of universities, and it's very exciting times. I'd say it's a highly promising technology, and there's a lot of lessons learned here that need to be further demonstrated. There's a lot of questions around where the heat can come, because the reaction for hydrogenation, the reaction for dehydrogenation requires a lot of heat. At this time, it's very tricky to couple those intermittent heat demands with steady heat sources from the iron and steel facility. So this is future work that could further improve not only the cost, but the carbon intensity of these systems, because they still rely on natural gas systems. And with that, I think I'm at time, and I'll hand it back to Rebecca.
Great, thank you so much, Hannah. I actually had a technical question I wanted to ask. What is the temperature requirement for the MCH system? And is there capacity for electrification there?
Yeah, that's a great question. And our colleagues, Dennis Papadias and Rajesh Lueni at Argonne, are looking into this for different carriers, whether they could be electrified. Our team is looked into it some, and we say the state of the art in electrifying that system is very low technology readiness level. And I didn't get into these slides, but one of the challenges is being able to have very careful control over the heat that is seen throughout the reactor bed. And today, direct heating with natural gas and electrification cannot provide the confidence needed to ensure you don't exceed temperatures that destroy your catalyst bed. And that catalyst is very expensive. So at this time, we are conservatively assuming only steam heating systems can provide that control that we need today.
Great, thank you. And I'll pass it back to Thomas and Steve.
Yeah, thanks for the
Yes. Thank you, Steve. Go
presentations. And
ahead.
yeah, Jen, this didn't show up in the chat, but your presentation, you focused on the continental US. And if somebody was interested in taking advantage of these analysis capabilities, is the analysis modeling, can you do that in other places? And what sort of data or information would you need to be able to do this in Asia or South America or Europe?
Great question. We have made it such that it should be easy to apply to other locations across the globe. The main things that we would need access to or some sort of data is wind and solar resource data. The other information, like if there's access to hydrogen storage, is really helpful, but we can at least make some assumptions and bounds and stuff like that. And then grid prices. So some of those input data streams are what we would need, but not impossible to get.
So is that hourly data from the wind
Hourly,
for a
yes.
year?
For a
And-
year.
And similar for solar irradiance?
That's right. We can do one of two things. Also, we can look at if you have predictions or whatever across a large time frame. So you can look at the lifetime of a plant, or we just take 1 year and repeat it every year for the lifetime of the plant. Thanks, Steve.
Hello, this is Carrie Rippey at NREL, and I'm co-moderating the question and answer session. We're getting a lot of questions in the chat about thermal management and specifically whether direct reduction could be electrified. Steve, I know you're leading work in this area, and also Hannah, I was curious if you had any work on modeling this.
Well, Steve, I'll let you take that question. On my side, we have not looked at the electrowinning or the electrification of the DRI system itself, but I know that's one of those future path options. However, I would say when surveying some prominent steel industries and looking at their portfolio for decarbonization, they really view DRI with natural gas and hydrogen as the very clear next investment, with the electrification as something much further down the line. And that would also really depend on us hitting our 2023 goals for decarbonizing the grid, because without that, you can actually increase your emissions.
Just to clarify, I think the questions are mainly focused on thermal management of direct reduction with hydrogen. So just electrifying the heating of that, not the actual electrolysis, although that is another interesting research avenue.
Well, it's certainly a endothermic process, and maintaining a steady heat for the kinetics at somewhere in the range of 900 to 1000 C is a big challenge. And I think most of the focus is on preheating the hydrogen, feeding that in and using that as a way to heat the iron ore. But as the volume of the furnace expands, getting a consistent heat to the iron ores, it's being reduced, but also producing the water vapor as a byproduct of the reduction process provides a bit of cooling. So you're sort of, a challenge in the effectiveness of the hydrogen as a heating agent, the cooling from generating the water vapor through the reduction process. You're sort of swimming upstream. So that's a significant challenge to be able to manage that, do it effectively, and then be able to dry the hydrogen once it comes out, separate the water vapor, and recirculate rather than having to always add fresh hydrogen completely back into your furnace.
Thanks, Steve. I also see we have a question that's generated several responses on the $1 per kilogram target cost of hydrogen. Maybe Thomas, if you could add some comments on that, it would be great.
Yeah, certainly. The hydrogen shot goal was announced in 2030, in 2021, with the goal of reaching $1 per kilogram by 2031. So it would 10 years to reach the goal. That was always an ambitious target, and with the impacts of inflation and supply chain constraints, it's become an even more ambitious target. But what we see is an enormous amount of interest in the technology and a lot of investment coming from both US and foreign companies into the United States to produce hydrogen at that scale. And so combined with the learning by doing economies of scale that we may see by the 2030s, with the hydrogen production tax credit, seeing a $1 per kilogram cost of hydrogen is certainly within reach. I will say there's a difference between what a cost of production is and what the selling price could be. So, we could see some spread there. And certainly it'll vary by region in the country, where you have really good wind and solar combined. That's maybe the best bet for reaching the low dollar per kilogram. In other parts of the country, that will be harder to achieve if you're not able to match up those resources in as good of a way. But that's certainly all informed by the great work that Jen has done in terms of integrating the modeling that we've invested in over decades as HFTO to really understand how to get the costs down. And so we're excited to see the industry finally taking off.
Fantastic, thanks. I was just going to ask if you wanted to add to that, Steve.
No, I was going to come to the hydrogen storage side. The question came up of how do you determine, this is for Jen, how do we determine how much hydrogen storage might be needed at a particular location?
Yeah, great question. So in our particular study, we determined this analytically by looking over the time series of the lifetime of the plant and making sure that we had enough storage to meet the demand at all times. Now, I will say this is a conservative approach because we didn't include, as I said during the presentation, we didn't include shutdown times or maybe times where loads might be reduced for demand purposes or other things like that. So this is maybe more of a conservative approach based on the map that was shown, but the same approach was used in all locations. One thing I'll mention too on the $1 per kilogram side of things, I think the inflation and the supply chain issues is a really interesting and important part to include, because when the hydrogen shot was set, those things were not in place at the time. And so right now, based on our modeling, without policy, we haven't been able to come up with a scenario where we can get to under $1 per kilogram. And that is largely due to those two factors. So yeah, just want to mention that and reinforce that.
Thanks, Jen. Continuing with the theme of hydrogen storage, we did get some early questions about different types of storage and what types of storage were considered and which were not in the slides that you showed. Specifically, I think there are questions about saline aquifers, lined rock caverns, and salt caverns.
Great question. We considered 3 different types of storage: salt caverns and lined rock caverns, which are location specific, and then compressed gas. So there's a huge range there and a huge opportunity for development, as Hannah was talking about, and we are working to include those in our modeling in the future, but right now that was limited. So one of the plots that we showed had Iowa and Indiana. They were even on the charts without policy, at least. And that spread had to do with using compressed gas as the form of storage. You can imagine if you have to do 15 days of storage in containers or even buried pipes, it's going to be a huge cost.
I also just want to add on that there's been, a lot of focus on salt caverns as the most cost effective, the cheapest. But the reality is, how many are actually operating today, and how much permitting and vetting is going to happen with those. So there's great potential in leveraging the subsurface. We're looking at all kinds of innovations in subsurface, yet having alternatives is critical if we're talking about getting things up and running in the next 10 years. And I have real concerns about our cost scaling factors for salt caverns, being way off. And I think we need to continue to push for alternative solutions for storage and really look at scenarios where no salt caverns are available and see what comes out of that, which is one of the reasons why the Highmark team is really trying to understand how we can create very safe above ground storage.
Thanks, Hannah. Kind of jumping off from that, could you comment on the trade-offs between storage and things like dynamic plant operation? I see we have a question in the chat regarding the fact that H2DRI could potentially have operational flexibility and that it could shut down over a number of hours or days. Did you model that at all?
Yeah, that was a great comment by Vincent, who's someone we consulted early on in this work, and I always appreciate his feedback. So yes, absolutely. If we are looking at industries that can ramp down and have flexibility in their hydrogen demand, that dramatically improves the cost because it decreases the size of what we call that dehydrogenation component of the storage system. And so it's a challenge without having the data to truly understand and provide security that the steel product is going to be at quality that the end consumer needs. Until we have that data, I think it's a question of just de-risking the market rather than a technical question.
Can I also add to that too? Just adding to what Hannah said, we did some analysis on that, and if you can have some of this flexibility, even if it is at this level, meaning like you can turn it off for a certain amount of days or reduce the load, really that takes away that seasonal storage component. So those huge numbers that were shown in the map are reduced significantly more to like 2 to 3 days kind of thing, instead of what we're looking at like 20 days. And that's a lot of that has to do with seasonal storage.
And I'll note that the scenario I showed was for 19 days of storage. So this is the most expensive, the largest scale system that we're looking at pretty much.
Thanks, Hannah and Jen. I think we have time for one more question, and we have a related question. Have you considered incorporating batteries?
Yes, excellent question. And it's something we are wrestling with currently. And there is a trade-off between using battery and hydrogen storage. And some of the limitations that we've come up against so far is just modeling capability is batteries are really good for short duration and doing things on a faster time scale, and hydrogen is not as fast. And so based on our just preliminary work, which I didn't show, there's going to need to be some hybrid approach, but we don't have specific numbers yet. Stay tuned. But yes, that's definitely a huge question. One of the other things that we did include, because we did include battery in some of our scenarios, is that it can help with resources that are not complementary. So if you have wind and solar at the same time, you often have like a huge stack of power, and then wind and solar both go away. So you have a lot bigger and steeper ramps, and batteries can help with that, those transition points. So again, more of a transient approach than like the seasonal storage that hydrogen would provide.
Well, since we are at time, Jen, Hannah, Steve, Carrie, thank you so much for presenting and for helping moderate discussion. And Steve and Carrie in particular for your leadership in helping this working group come together. To all of our attendees, thank you for being here, and stay tuned. We have a lot more to come. Have a great rest of your day.
Thank you.
Thank
Yeah.
you.
Thank you.